now recording the session. And I'm going to get the PowerPoint back up for Chapter 9. Okay, let's try it this way. One more time. Okay, I'm hoping that everybody can see this.
Yeah.
Okay, very good. So this is the idea here. This is one of the examples in the book, and it goes through a use of confidence intervals for a proportion, okay? A proportion. We're taking this number right here, 567, and we're dividing it by 1,031. So this is going to be a proportion. What is the population proportion? What is the symbol for the population proportion?
P hat.
Okay, P hat is a good guess, but P hat is going to be the sample proportion, and P is going to be the population proportion. Okay, does that make sense? Okay, so here we're looking for the population proportion, and we want to use a sample to actually estimate that population proportion P. So 567 over 1,031 will be the number, the value of P hat. Okay, so here is P hat, and we have plus or minus a critical z-score. This is the margin of error, the standard error that goes along with this, this general formula. Okay, so this here, the book uses this complicated phrase, bound on error estimation. I really don't like that. We're going to use the words margin of error, okay? So the critical Z times the standard error is going to give us the margin of error. All right, so in our example, here's P hat, and here is the number that were surveyed out of a sample of 1,031. So 0.55 is the P hat in this problem. So what is the 95% confidence interval for the population proportion of adult Americans that goes along with this problem? All right. Are you still following me?
Yeah. Yeah.
Okay, very good. So here are the conditions. These are the assumptions that we're thinking about, okay? So the sample size has to be large enough, and these are some of the ideas that go along with the population. So we have p hat, then we have 1 minus p hat here to get 0.45, and both of these numbers here, both of these numbers here are greater than 10. So we have a large enough sample size. All right. So we have a great population, all the adults in America, and we want to make sure that we have a random sample from the population. So these conditions have to be adhered to before we even try to build a confidence interval. So all the conditions are verified, and we can go ahead and start to calculate the confidence interval. So what does 1.96 mean? What is that? Where does that come from?
That's the z-score that goes along with the 95%.
Okay, so 95% is the confidence level we want. And if we go back to the empirical rule, 95% is 2 standard deviations away from the mean. And we have to look at 1.96 as 2 is pretty close to that, all right? And so if we were to take the estimate is p hat, and we're starting to think about that as a value that might be very close to the population proportion. All right, and here is the confidence interval. Here is the low end, and here is the high end of the confidence interval. Now, let me ask you this question. This term right here, what is that called?
The margin of error.
The margin of error. Very good. Okay, so everybody's following along. The margin of error. So if we were to conclude something here, interpret this confidence interval, we start out with the sentence, and I try to tell people to actually use this type of language. We are 95% confident that the population proportion, and then we fill in the blanks of adult Americans who have college education is essential for success between, this would be 52.1% and 57.9%. All right, so start out with your confidence level with the conclusion. Make sure that you introduce the population parameter. In this particular case, the population proportion is the parameter that we're looking for, and end the interpretation with your results coming from the margin of error. Does everybody understand what I'm suggesting here?
Yeah.
Okay, so we want to do not only the calculation, and that's very important. I'm not suggesting it's not important, but we also want to interpret our findings in a appropriate way. Okay, so how about what would happen if we had a 90% confidence interval? Same sort of setup, but what happens to the interval? First, tell me what we want to do in terms of changing this sort of formula here. What's the first thing that we want to do?
Change the z-score.
Change the z-score. That's right. Now, is the z-score going to be higher or lower? Is the 90% confident, the 90% confidence, is the z-score associated with this number going to be lesser or greater than this one right here?
Maybe
Would it be less than?
Less.
Okay, less than, all right? So less than is the answer. So here is the z-score for 90%, and it is smaller. Okay, now I'm going to ask you, does the confidence interval for 90%, does that get wider or more narrow?
More narrow.
More narrow, okay? And that's based on changing this value to this value right here. And of course, if you had 99% confidence interval, what would happen?
Would it get wider?
The confidence interval would get wider, okay? Now, let's start to think about this a little bit more. Now, if we're looking for an unknown parameter, okay, an unknown proportion, okay, do we have a better chance of getting, of capturing that population proportion? Do we have a better chance of getting the population proportion with a 99% confidence or with a 90% confidence? Okay, so it would be more likely that we would capture the population proportion with a 99% confidence, which is very wide, versus a 90% confidence, which would be very narrow. Okay, right?
Yep.
Okay. So just for our purposes, this is the z-score that goes along with 99% confidence. So we go from very, very wide to medium wide, and then the more narrow confidence interval. Questions about that? Okay, so since we have sort of a margin of error, okay, I'm going to focus on the margin of error. And what I'm going to do is I'm going to start to think about choosing an appropriate sample size for our estimate. Now this here, right here, bound on error estimation, I'm going to change that to the margin of error, right? So we have a margin of error for a 95% confidence. Then we can start to think about this being the margin of error. This term right here is the margin of error. We can use B, but I would prefer using ME. ME being the margin of error. So what we can do with this margin of error, if we have sort of an idea of what the margin of error will be, then we can actually understand how big of a sample size we need just by isolating the sample size n. So this is one piece of information that might be helpful for you as you go along with the rest of your career here and statistics. So getting a sample size, selecting a sample size can be determined by this term right here if we have a sense of the margin of error. I'm sorry, yes, the margin of error, right? Okay. So P is still unknown, all right? So we probably want to go and start to think about how we could find out some information about the population proportion, or P. Sometimes we get to use a preliminary study to get an estimate of P. Sometimes we can use prior knowledge that goes along with an estimate of P. If we don't have any foundation for what P might be of a population, then we can be using a process that is very, very conservative, okay? If there's no prior knowledge of the preliminary study, we want to use the margin, or we want to use the proportion 0.5. And why is 0.5 something that is conservative? Why do we want to use 0.5 as the estimate of P? And I'll show you that in the next slide. So let me just get away from this. So we're really looking at this idea right here. We could set P as 0.1, 0.2, 0.5. That's our privilege, but we want the most conservative estimate of P. So if we were to use 0.1 for P, this would be the product of P times 1 minus P. So 1, and then we're going to go 0.1 and 0.9. And again, if we were to use 2 as P, then 1 minus P would be 0.8. If we use 0.3, 0.7 would be 1 minus P, and that would be 0.21. Do you see a pattern growing here? We're going from 0.09 through 0.16, 0.21, and we could use 4, 0.4, and 0.6, but the most conservative product of P times 1 point, I'm sorry, let me say it again. P times 1 minus P would give us a number, the most conservative number along with this, 0.25. Questions about this? Okay, so by using P, using 0.5 for P, we have the largest value for this term right here. P times 1 minus P is what we're looking for in our calculations, a very conservative value. Okay, so here is an example, all right? We have potential safety hazards. Some people are using the internet in their car. Determine the sample size required to estimate a proportion of the adult Americans, okay, that would like an internet connection in their car is within 0.03. 0.03 here represents the margin of error. And we want to know that under the umbrella of 95% confidence. So that value right there is the margin of error. And if we were to start to use simple algebra to isolate the n variable, okay, that's the sample size. This would be the outcome that goes along with this. So we're going to put 0.5 as the population proportion, and then that would be 1 minus P would be 0.5, and B here is the margin of error, and that's going to be 0.03. All right, so if we do this, we multiply this here, 0.5 times 0.5 gives us 0.25. Here is the margin of error. Excuse me. And here is the Z-score for 95% confidence. And with this in mind, we get a sample size of 1,067 with some numbers that are the quotient of that. So we want to always, in this particular case, we want to be conservative, and therefore we want to always round up, okay? Always round up with a sample size and make it a whole number. Questions about measuring the sample size? Okay, so let's sneak into this one last bit of information. We want to apply the same things that we've been thinking with in terms of a population proportion. Now we want to start to think about a population mean. And we want an estimate of an unknown population mean. All right, so mu is unknown. All right, so let's go through the general formula here. X bar is the sample mean, okay, and that's going to be our estimate. X bar is going to be our estimate for our unknown population mean. So the sample has to be a random sample. The sample size of n is large. It's got to be greater than or equal to 30. We have some knowledge, or we have a number that's given to us that represents sigma, the population standard deviation. That's known. So these are the properties that we start with when we're thinking about a distribution of sample means. So this needs X bar is the bars over here. All right, so here is the general formula for a confidence interval directed at the population mean mu. So the estimate of mu is X bar plus or minus this critical Z value. Here's the population mean, the population standard deviation, and we're dividing that by the square root of the sample size. So that's the point estimate. Here is the standard deviation of the distribution. This could be said, this term right here is the standard error. Okay, the standard error. And then this here is the margin of error. This product with the z-score and the standard error turns into the margin of error. It's probably not typical that we, if we don't have the population mean, we probably don't have the population standard deviation either. That's real life. Okay. So we're thinking about a population that is normally distributed. All right. So if we have a sample size that's greater than 30, then we assume that the population distribution is normally distributed. Okay, so here is our example here. We're thinking about cosmic radiation levels and polyps that fly in high altitude. Okay, a study brings a sample of 219 millirems, and that is our X bar, 219 millirems. We have a sample size of 100, and the standard deviation of the population is 35. Calculate and interpret a 95% confidence interval of the actual mean annual cosmic radiation exposure with this flight of crew members. So we have to verify many of these examples, these conditions. It's a random sample, so that's good. It's a sample size that's greater than or equal to 30. And we have the sigma value, the population standard deviation of 35. All right, so these are the three different things that we need to put together a confidence interval for a population mean. Calculate and interpret 95% confidence. We're using X bar plus or minus this, the Z critical value, the standard error here. So we're using 219 plus or minus 1.96. That goes along with 95%. Population standard deviation is 35. Sample size is 100, and we're taking the square root of that value. And here is the confidence limits that go along with this. So here's the low end, and here's the high end of the confidence interval. Okay, so let's think about this in terms of context. So we have the values, just like I was saying minutes ago, we have the confidence interval, we have these values, but now we want to put them into context. We want to interpret our findings. We are 95% confident. That's the phrase that starts the conclusion. And then this phrase here starts to reiterate what we said up here, okay? For actual mean annual cosmic radiation exposure with this crew, and then we end the interpretation with the values that go along with the confidence interval, the small end and the large end of the confidence limits. Questions about this? Okay, so what would happen if the width, what would happen to the width of the interval if the confidence level changed from 95 to 90% confidence? What happens to the width of the confidence interval?
Would it become wider since the confidence is decreasing?
Okay, so let's think about this. Now, Logan, what is going to be the z-score for 90%? That value is 1.645, okay? Compared to the z-score for 95%, that's 1.96. So actually, it sort of will narrow the confidence interval, okay?
Okay.
Just because the z-scores that go along with those 90 and 95%, that's what's controlling the width of the two confidence intervals.
Okay.
Okay, last one here, all right? So here we are, carbon and forest biomass, all right? So scientists are hoping to curb deforestation and getting sort of an estimate of the carbon that would be stored in the tropical forest across the globe, okay? And they're estimating that there is 247 gigatons of carbon stored in those regions. Okay, for sure we don't know the population mean, okay? So if we want to get an estimate, we first need to get a sample, and we're going to use those samples within a square kilometer. So we're estimating the amount of carbon per squared kilometer. Okay, based on this sample size, 4,779 different plots were chosen. Okay, so the sample size is really, really large. All right, we have a sample mean of 11,600 tons. and the standard error is 1,000 tons. Okay, and we want to build a confidence interval around the estimate to give us a sense of what might be the population or all of the sources of biomass. How would we put this together? So we want to create or calculate a set of values that go into a 95% confidence and then interpret that level. So what do we start with? Well, we start with the estimate, right? And we'll go over here. And so here is the X bar, 11,600. All right, here is the plus or minus. Here is 2. Now 2 is very, very close to 1.96. So 2 is being used to substitute for 1.96. Here's the standard error at 1,000. And these are the limits to that confidence interval. And how do we interpret this? We are 95% confident that the average amount of carbon stored in each squared kilometer in these tropical forests, and it's between 9,600 to 13,600 tons. Questions about that?
So yeah, I do. Why would you round it to 2 if it was 1.96?
That's a great question. Okay. I would use 1.96. The only reason to do it is because 2 is a bit easier to deal with than 1.96, but stick with 1.96.
Okay.
Okay. Good question. Other questions? Okay, so I'm going to call this the last slide that we're going to use for the upcoming exam. Okay, so there's a lot left into Chapter 9. I'm not going any further, and I won't test you on anything past this example. Does everybody hear what I'm saying?
Yes.
Okay, so when I put it up, I'm going to put all of Chapter 9 up, but slide 33 is the last slide in this topic.
And then just to confirm for the exam,
Mhm.
it's chapters 8 and 9, right?
8 and 9, yes, sir. Yes, ma'am. Other questions? Okay, let me iterate one last time. It's been a real honor to help you guys out with your futures, and I am really, really happy with the work, the work that you put in, and the diligence that you've shown yourself to get through this unprecedented situation in our country and world. So great job, guys.
Thank you.
Thank you so much.
Thank you.
Thank
Have a
you.
good day, and
You too.
Thank
and
you.
we'll see each other in a week or so.
Okay, thank you.